Welcome to our Rare Earths for Our Energy Futures Tour. I'm Mary Hemmingsen, and together with Calitz and Jared Manz, we're pleased to host this session, and thank you for joining us. Rare earth elements, neodymium, praseodymium, dysprosium, terbium, and lanthanum form the performance critical core of modern electrification. Respectively in their chemical names, Nd, Pr, Dy, and Tb, they enable high-strength permanent magnets at the heart of the EV traction motors, onshore and offshore wind turbines, HVDC systems, and advanced industrial motors. Lanthanum, while not a magnet element, is equally foundational in battery alloys, grid materials, and emerging storage chemistries. Despite the name, rare earths are not geologically rare. What is rare is the global capacity to economically extract, separate, refine, and manufacture them in an environmentally responsible way into high-performance materials, a capability and footprint concentrated in only a handful of regions. Currently, the footprint of extraction is energy-intensive, chemically laden set of steps, and with the result that it also produces toxic waste, some of which is radioactive. While each EV motor uses only grams to hundreds of grams of magnetic materials, a multi-megawatt wind turbine uses 10 to hundreds of kilograms, and scaled across millions of vehicles, gigawatts of wind, expanding grids, and high-efficiency industrial systems, these relatively small inputs compound into enormous system-level demand. Today, the energy transition is the dominant source of new demand for these rare earths and a growing driver of demand for lanthanum in the next generation catalytic processes. This accelerating demand, coupled with the realities of sourcing and processing, raises critical questions. Where do these minerals come from and who controls the choke points? How do environmental and social considerations shape responsible, scalable development? How resilient are supply chains to geopolitical shock, trade restrictions, and technology shifts? What alliances, investments, and policies are required to diversify supply? And which technologies, recycling, substitution, new magnet chemistries, alternative battery minerals may shape long-term demand? These questions and their answers define the direction of travel for energy security, industrial competitiveness, and climate goals. With China controlling more than 85% of processing and magnet manufacturing, exposure to supply disruptions and price volatility is real and growing. So today, we will survey the landscape and journey to the front lines, touring major mining and processing regions to understand the players, positions, and pressures shaping our energy future. We'll map vulnerabilities, explore emerging strategies, and build insight to better engage and influence the actions required to secure supply. So over the next hour, we'll travel to China, the US, Canada, Greenland, Brazil, India, Myanmar, and Australia, from mines and separation facilities to magnet manufacturing hubs, exploring the constraints and opportunities defining rare earth supply. Please post your questions in the Zoom chat, fasten your seatbelts, and kindly mute your audio as we begin. Let's start by mining our periodic table for these 5 rare earth elements known for unique electronic configurations that enable exceptional magnetic properties, and see that they sit in the lanthanide series of 15 elements on the second row from the bottom. For completeness, there are 2 others in the upper left, all circled in red. Although often found together in geological deposits, La, Pr, and D are light rare earth elements, LREEs, while Tb and Dy are heavy rare earth elements, HREEs, a distinction that reflects major differences in abundance, processing complexity, and strategic vulnerability, which we will feature in our tour. These elements are indispensable in forming NdFeB, iron-bearing permanent magnets, the strongest commercial magnets available. These neodymium-based magnets, while traditional magnets, unlike traditional magnets, don't lose magnetism when exposed to constant electric current used to turn motors on and off. So together they make possible the high-performance electric motors and generators that underpin modern clean energy technologies. Within magnet chemistry itself, the elements Nd, Pr supply the bulk of the magnetic strength. La plays a supporting role in select magnet and alloy formations, while Dy and Tb are used in very small proportions but carry disproportionate strategic importance because they deliver the high temperature stability required in EV drivetrains and offshore turbines, where performance margins are tight. Now over to Jared to show key applications across the group.
Visiting the marketplace, this diagram shows how a small group of rare earth elements underpins three major sectors: energy, defense, and AI. Although there are 15 lanthanides, only a subset drives system-level performance and risk. At the center are neodymium and praseodymium, which provide magnetic strength, and dysprosium and terbium, which deliver the high temperature stability required in EV drivetrains, offshore wind, and advanced defense systems. Lanthanum can play a supporting role in select magnetic and alloy formulations, while elements such as yttrium, cerium, europium can support optical, phosphor, and advanced electronic applications. Together, these materials enable the core hardware across energy systems, national security tech, and AI infrastructure. Because these sectors converge on many of the same rare earth elements, supply disruptions would not be isolated. They would ripple across all three simultaneously. And with that framing, Andy will now discuss production trends.
Global rare earth production is actually quite small compared to, say, bauxite or copper, but we can see that rare earth production tripled from 90 to 270,000 tons after 2000, accelerating quite clearly after 2010 as permanent magnets became central to clean energy technologies. Let's take a look at the global rare earth industry. On the left, we can quite clearly see the 14 countries that play significant roles, from China at the top to Russia at the bottom. On the bottom, we can see their positions in reserves, in mining, in separation, in metal and alloy production, in magnet production, and EV and wind turbine manufacture. And from this picture, it is quite clear that China dominates every column: reserves, mining, separation, metal alloys, magnets, and EV and wind pool. And so China is the true choke point in the midstream. Australia, the USA, Myanmar and Brazil, India and Canada have credible mining pipelines, but very limited integration today. And Japan and Korea and Germany show a strong manufacturing pool, but they rely very heavily on imported rare earth inputs. Our tour today starts in China. And China's advantage is that full stack system that we saw on the previous picture, because of its strength in mining, concentrate, separation, metals, magnets, and downstream manufacturing. And the headlines about China and rare earths tell us that story. We see China tightens export controls on rare earths processing technologies. We see Beijing signaling rare earth policy shift amidst growing US-China tensions. We see China's rare earth refiners expanding their capacity as the global demand accelerates. And we see global governments, on the other hand, accelerating their de-risking plans from China and its rare earth grip. We see that China's magnet industry is reinforcing its dominance in NdPr and heavy rare earths. And we see that environmental crackdowns are reshaping the rare earth mining provinces of China. Let's visit 4 places in China: the Bayan Obo mine in the north in Inner Mongolia, and just south of that, the Baotao rare earth industrial zone, also in Inner Mongolia. Then we travel south to the ionic clays on the Chinese coast, and we visit a magnets factory in Ningbo. Bayan Obo in Inner Mongolia, that we see below us, is the world's largest rare earth mining complex, integrated with major iron production. It is operated by Baogang. It feeds the Baotao rare earth processing and magnet manufacturing ecosystem through the railway line that we can see traveling to the south. The output is light rare earth dominated, lanthanum and cerium by volume, plus neodymium and praseodymium for magnets. And the co-products of iron and niobium materially shape the economics, buffering this mine from rare earth price cycles. Arriving in Baotao, let's remind ourselves that rare earths are fundamentally a processing industry and not just a mining industry. From 200 kilograms of ore, most mass becomes iron oxide and waste, while only small quantities become high-value magnet metals like neodymium and dysprosium. After crushing and grinding and magnetic separation and flotation, the rare earth concentrate is chemically cracked by roasting and leaching, and the real complexity begins in solvent extraction, where multiple stages separate light rare earths such as lanthanum and cerium from neodymium and praseodymium, and then heavy rare earths like dysprosium. And those final steps include complex precipitation, complex calcination, and electrolysis into metal. And China is just so competent now at managing this chemistry of the operating system to do this. Arriving in Baotao, we see the world's most concentrated rare earth industrial zone, fed by an obo via a dedicated railway line that we see coming in from the north. The core advantage is not only mining, but the full chain: cracking, separation, refining, and magnet supply. And we can see that the landscape shows the scale, the dense processing plants, the rail logistics, the large process water systems. And that Waikang tailings dam that we see on the left is the zone's defining environmental legacy, storing decades of chemically treated residues. The residential districts sit close to the industry, highlighting the social and regulatory sensitivity. But Baotao illustrates why China's rare earth dominance is built on this processing ecosystem, not just ore. Traveling south, we can see the thousands of small ionic clay mines of southeastern China. And these clay deposits yield heavy rare earths, dysprosium, terbium, yttrium, very efficiently. They are weathered granites, and simple leaching extracts rare earths without the usual hard rock mining. And those products feed the Chinese magnet supply chains: neodymium, praseodymium, and all the other critical heavies so important for EVs. The environmental concerns include ammonium sulfate leachates into water systems, so that leads to water contamination, and a great deal of illegal artisanal operations exist. And China's processing dominance means that these clays reinforce pricing power and its export leverage globally. China leads the world in neodymium iron boron magnet quality through scale, tight process control, and decades of engineering learning curves. And the advantage is not just REE supply, it is the sintering, the coating, the machining, and the ultra-low defect rates in their manufacturing processes. China clusters integrating alloying, powdering, magnet making, motor making, and testing in one ecosystem. The city of Ningbo is one of China's top magnet hubs, supplying EV motors and wind turbine generators. And the Tongshuan magnet company strength is its high performance grades, consistent quality, and high volume delivery. But Ningbo also has that Chinese cluster, giving Tongshuan nearby access to metals, to tooling, to coating, and motor customers. So after China, take us to the United States, Mary, the main rival to China in rare earths.
Thanks, Andy. And here in the US, in response to China ruling the world, the rebuild is to secure feedstock, expand commercial scale separation, and reestablish magnetic production after decades of offshoring. Project Vault, a proposed strategic mineral stockpile funded by almost $2 billion in private capital along with $10 billion from the U.S. Export-Import Bank loan, seeks to turn the tide. And with further backing by the Pentagon and major automakers, new projects aim to deliver domestic NdPr oxides and eventually finished magnets to reduce reliance on Chinese supply for EV drivetrains, wind turbines, and industrial motors. But significant permitting delays highlight the tension between urgency and environmental expectations, and U.S. policy continues to rely on subsidies to bridge capability gaps. Let's visit Mountain Pass in California, MP Materials in Texas, and White Mesa in Utah. Mountain Pass in San Bernardino County, California is the United States' only scaled, fully integrated rare earth mine and processing plant. Operated by MP Materials, it is built on an open-pit bastnäsite carbonatite deposit, one of the world's richest sources of light rare earths. The site performs end-to-end production, mining, milling, flotation, separation, and refining, an uncommon level of integration outside China. Since 2022, Mountain Pass has been recommissioned and expanded its separation and refining, producing high-purity rare earth oxides, including NdPr, essential for high-strength permanent magnets used in the EVs, wind turbines, electronics, and defense systems featured earlier. Mountain Pass today supplies more than 10% of global rare earth materials, making it a central pillar of Western supply chains. It historically exported concentrate to China, but is now being reintegrated in a U.S. mine-to-magnet strategy as federal funding and defense demand drive efforts to rebuild domestic refining. White Mesa Mill in Utah, operated by Energy Fuels, is the only licensed uranium mill in the U.S. and the only U.S. facility producing monzonite into separated rare earth oxides, including light rare earths like NdPr oxide. It has now begun pilot-scale heavy rare earth production, including dysprosium and terbium, making the U.S. output of mined heavy RRE oxides feedstocks. Feedstock comes from byproducts sourced in the U.S. and Australia, but heavy RRE volumes are small and early stage, with commercial production targeted for 2026, making White Mesa a strategic build-out in the midstream processing hub aspirations of the U.S. MP Materials Magnet Facility in Fort Worth, Texas, the Independence plant, produces NdPr metal and is ramping trial productions of sintered magnets, making the first large-scale U.S. magnet manufacturing effort in decades. Its direct tie to Mountain Pass, which supplies the NdPr oxide and rare earth concentrate, creates a linked U.S. mine-to-magnet chain. Before we leave the U.S., let's look on the horizon, where U.S. rare earth development is focused on expanding refining capacity, building a circular supply chain with recycling, and expanding domestic magnet production, all fraught with scaling, capital, and permitting risk. Notable developments are at MP Materials, which we visited, scaling to additional magnet capacity at its Texas Independence plant and tied directly to increased NdPr supply from Mountain Pass. New heavy rare earth capacity is emerging, with Energy Fuels White Mesa Mill seeking commercial scale output of Dy and Tb, a major step, early stage, yet capital intensive. On the circularity front, ReElement and Electronic Recycling International's partnership is building a domestic recycling to refining pipeline. ReElement is already producing pilot-scale 99.9% pure REOs at its Noblesville, Indiana plant and plans to shift commercial production also to an Indiana plant starting in 2026. Other notable developments are MOUs at the pre-FID stage. We will monitor these efforts to build a complete non-China mine-to-magnet chain.
Arriving in Canada, where I spend most of my time, Canada's rare earth story is about processing-led diversification at a continental scale. It combines large underdeveloped resource potential with political stability and strong alignment with Western supply chains. Multiple projects across the country are moving forward, while downstream processing capacity is taking shape. As global demand rises, Canada's accelerating rare earth exploration, particularly in systems rich in heavy rare earth elements. Those projects are drawing growing strategic attention from allied countries looking to diversify supply. At the same time, Canada's processing ambitions face financing and scale challenges, highlighting both the opportunity and the work still ahead. In around 2020, government supported development of Canada's first integrated rare earth processing facility in Saskatoon, operated by the Saskatchewan Research Council. The goal was to help establish a domestic mine-to-metal supply chain, and the facility has already processed some of the concentrate from Canada's only producing rare earth mine, Nechalico, in the Northwest Territories. In 2024, the Saskatchewan Research Council achieved Canada's first commercial production of NdPr metal. The plant is ramping up, with full commissioning expected by the end of 2026 and steady operation in 2027. At capacity, it's expected to produce about 400 tons per year of rare earth metals, enough magnet material for hundreds of thousands of EVs annually. The facility now has a US offtake agreement and is studying expansion. Future feedstock could come from Saskatchewan deposits, supporting a provincial mine-to-metal supply chain. Chalico remains Canada's only site to have produced rare earth concentrate through a small starter campaign in 2021 and 2022. Attention is now focused on the larger nearby Tardif deposit. A 2025 scoping study outlines potential production of 56,000 tons per year of high-grade concentrate, roughly 10 times the previous levels. A pre-feasibility study is targeted for 2026. Canada has several additional rare earth projects advancing. Strange Lake in Quebec and Labrador is a large heavy rare earth deposit rich in dysprosium and terbium. The project envisions an open pit mine with an on-site concentration plant, a roughly 170-kilometer road to a new port on the Labrador coast, and a separation plant in Sept-Îles, Quebec. With feasibility and permitting work advancing, it represents one of the few potential future heavy rare earth sources outside China. Wichita in British Columbia shows strong viability, with planned production of about 32,000 tons of total rare earth concentrate per year over a 15-year mine life, and potential production later this decade. Alsace Lake in Saskatchewan is earlier stage, but high grade and located closer to the Saskatoon processing facility. Hoytis Lake in Saskatchewan is another important deposit under evaluation and has a direct strategic link to the Saskatoon processing facility, positioning it as a potential future source of provincial feedstock. Together, these projects, along with others at earlier stages, show that Canada's rare earth story is about a diversified development pipeline that could support a meaningful long-term supply chain. Next, we travel all the way to Australia, and I'll hand over to Mary.
In visiting Australia, we see Australia's position in rare earths, anchored by reliable feedstock as it seeks to onshore a supply chain. In the headlines, we see the high-grade Mount Weld deposit featured as the cornerstone of Western rare earth processing capability. Building on that foundation, Australia's ambitions now extend beyond mining, with Lynas delivering the first commercial production of separated heavy rare earth oxides, such as Dy and Tb, outside China. As well, Australia is funding rare earth downstream processing to build magnet supply resilience, where new cracking, leaching, and separation investments reduce the need to ship concentrates offshore for processing. The emergence of Australian Nuclear Science and Technology Organization's pilot plant and other facilities underscores this gradual move towards domestic supply chain capabilities, even as full-scale capability is still developing. In parallel, Australia rare earth miners are seeking long-term offtake deals with the US and Japan to harness strong geopolitical demand, yet securing these arrangements doesn't eliminate the infrastructure constraints and commissioning delays. And despite ambition, high-profile developments such as the Nolans Project mine reveal the financing dependencies that can slow strategically significant developments, keeping Australia's ascent measured rather than meteoric. Let's briefly tour Lynas Mount Weld mine in Western Australia, where one of the world's highest grade rare earth deposits feeds the new 800 million Kalgoorlie processing facility. Here, at Australia's first rare earth cracking and leaching plant and the largest outside China, we see Mount Weld concentrate converted into mixed rare earth carbonate for downstream separation. Together, Mount Weld and Kalgoorlie form the core of Lynas ex-China mine-to-carbonate supply chain, materially strengthening Western resilience in Nd, Pr, Dy, and Tb. Kalgoorlie is Lynas' cracking and leaching step, turning Mount Weld concentrate into mixed rare earth carbonate, MREC. This MREC is then shipped to Lynas Malaysia, given for separation into saleable rare earth products. The site matters because it moves more processing onshore in Australia, reducing reliance on offshore intermediate steps. However, one of the operational challenges is that repeated power disruptions have reduced the MREC output and flowed through to Malaysia volumes. However, mitigation is underway, and Lynas is accessing off-grid power options and working with the Western Australia utility to stabilize supply. On the horizon, Australia is pushing to become one of the leading ex-China rare earth hubs. In addition to real progress evident in the recently commissioned Kalgoorlie plant that we visited as the largest outside China, other, more nascent developments include Kopamura, Australia's first major ionic clay deposit project, advancing through test work and regulatory steps and aiming for a mining lease in 2026 and pilot processing via Australia's Nuclear Science Technology Organization support, with earliest development later in the decade. An Abbott refinery backed by a $1.65 billion government loan is moving forward to commissioning and becoming Australia's first fully integrated rare earth refinery, despite cost escalation and timing delays. Further north, at Nolan's project, the planned supply 4% of global NdPr has been pushed to a long-awaited final investment decision, as we noted at the outset, to the first half of 2026, with construction poised to take place 37 months after. Australia's ambition is clear, a sovereign value-added rare earth supply chain, but the reality is Australia is progressing, but timelines remain long, capex is rising, and full mine-to-magnet independence is years away. In visiting Malaysia, we see it matters because, as we noted in our Australian tour, Malaysia hosts a critical separation step for Mount Weld field. And as a key rare earth processing hub outside China, Malaysia is increasingly reinforcing this role, a position anchored by Lynas Malaysia, whose operations remain central to global rare earth supply. And as geopolitical pressure mounts on China-centric supply chains, Malaysia's processing capacity becomes even more strategic, prompting the government to sign critical minerals cooperation agreements with major partners seeking stable and diversified access. At the same time, Malaysia is weighing new incentives to expand its downstream rare earth industry, aiming to capture more value onshore and strengthen its position in the global magnet-to-materials ecosystem. Yet, rare earth regulations and waste handling remain flashpoints, shaping both local sentiment and investor confidence. Against this backdrop, global investors are tracking Malaysia's policy signals closely, recognizing that decisions made in Kuala Lumpur will meaningfully influence the resilience and direction of non-China rare earth supply chains. So let's see Lynas Advanced Material Plant on the ground. Located in Gebeng, the plant currently operates as the core separation hub for rare earth materials originating from Mount Weld in Western Australia, as we've mentioned. Historically, all Mount Weld concentrate was shipped directly to Malaysia, where the plant carried out the full cracking, leaching, solvent extraction, separation, and finishing processes. Today, some of that upstream processing has shifted to Lynas' new Kalgoorlie cracking plant, which now pre-processes part of the material before sending mixed rare earth carbonate to Malaysia. This reduces the volume of radioactive residues imported and lowers the chemical burden at the Malaysia plant. The Gebeng facility still handles the key midstream step, separating valuable light rare earths, primarily Nd and Pr, essential for EV motors and wind turbine magnets. Environmentally, Malaysia faces challenges tied to residue management, chemical use, and public scrutiny, given past controversies over radioactive and wastewater risks, issues aggravated when cracking was fully done in Malaysia. Although Kalgoorlie now reduces part of that load, ongoing regulatory and community pressures remain high. On the horizon, Malaysia's most significant concrete step forward is the heavy rare earth separation expansion at Lynas Advanced Material Plant. Additionally, the government strategy under its national mine-to-magnet policy seeks to consolidate Gebeng as Malaysia's combined rare earth element and magnet manufacturing cluster under a partnership being finalized with South Korea's JS Link, planned to be located adjacent to existing separation expansion. As well, the policy looks to support domestic mining from ion absorption clays, estimated at over 16 million tons in various locations between 50 to 800 kilometers from the Lynas site. But progress is slow due to environmental restrictions, 94% of these potential resources lie in forest reserves, and setbacks such as illegal mining and compliance failures highlight that domestic feedstock development remains a long-term, high-risk path.
India's rare earths pathway runs through regulated monazite beach sands and a renewed state policy push for processing and manufacturing those beach sands and its national scaling intent. And in the news headlines, we see that India moves to secure rare earth supply for EVs and wind turbines, as they've done for so many other energy transition equipment, that New Delhi reviews rare earth processing expansion plans, that India seeks partnerships to reduce its dependence on Chinese rare earths from the north, and that rare earth exploration gains urgency under India's critical minerals agenda. But we can also see that downstream India's magnet manufacturing ambitions face rare earth separation bottlenecks. Those are just so complex. I'm going to visit two places on the Indian coast, Chhatrapur in Odisha state in the northeast of the country, and Shivara in Kerala in the southwest of the country. The Irel company is formerly the India Rare Earths Limited, and it spearheads India's rare earth production. And here at Odisha Sands at Chhatrapur, we see India's flagship beach sand and mineral operations feeding the rare earth supply chain. It mines and separates heavy mineral sands, especially ilmenite, rutile and zircon, but also monazite from these coastal deposits that we can see below us. And monazite is the key rare earth bearing mineral containing mostly light rare earths, cerium, lanthanum, neodymium and praseodymium, but also importantly radioactive thorium, which drives tight regulatory control. These concentrates move into Irel's downstream processing network for rare earth chemicals to be used in magnets, polishing powders and catalysts. And the Odisha Sands complex illustrates India's strengths: secure monazite resources, but also its constraint, the complex thorium-linked permitting and very slow scale-up. Here in Kerala, we see Shivara Kollam, which is India's most important coastal heavy mineral sands district for monazite and rare earths. Irel mines these beach sands and concentrates them into ilmenite, rutile, zircon, garnet and monazite, and we can see the operations. This is a strategic domestic feedstock for India, but the volumes are very small compared to China and Myanmar, as we will see later. And the key constraints are the radiation controls, community sensitivity, and strict regulation of monazite handling. So from India, Jared, take us to Brazil.
Emerging ionic clay source of heavy rare earths. Brazil is positioning itself as a potential new supplier of heavy rare earth elements through ionic clay deposits similar to those found in southern China. Brazil's ionic clay rare earth projects are attracting global strategic interest as the country positions rare earths as a pillar of its broader critical mineral strategy. At the same time, the United States and Brazil are exploring cooperation across rare earth supply chains as part of a broader diversification effort. Brazil aims to move beyond mining into refining and magnet production, although projects face familiar infrastructure and permitting hurdles. Brazil's only producing operation is the Serra Verde ionic clay project in Goiás. It's one of the few operations outside Asia producing both light and heavy rare earths at commercial scale. Production began in 2024, with Phase 1 designed for at least 5,000 tons average per year of oxide equivalent concentrate. Serra Verde is ramping up towards 6,500 tons per year by 2027, with a potential Phase 2 expansion that could roughly double output before 2030. The project has secured significant U.S. financing to support expansion and integration into Western supply chains. Brazil also has a strong project pipeline. The Carina project in Goiás is an ionic clay, heavy rare earth rich deposit moving through feasibility, and the Caldera project in Minas Gerais is one of the highest grade ionic clay discoveries globally and has advanced through early permitting and pilot production. Brazil remains underexplored, and with supportive geology and increasing allied financing, could become an even more meaningful supplier if infrastructure and permitting constraints are addressed. Now over to Andy as we visit Myanmar.
Unstable Myanmar needs to be handled very carefully. The significance is its upstream influence in heavy rare earths, but the processing gravity across the border in China. And the headlines reflect that. We see Myanmar remains a key supplier of heavy rare earths into the Chinese supply chain. We see that rare earth mining in Myanmar draws increasing environmental scrutiny, that trade disruptions threaten heavy rare earth flows from Myanmar, and that Myanmar's rare earth output becomes strategic amidst the global magnet demand. However, analysts warn of supply risk from Myanmar's unstable mining regions. Down at Myanmar, which sits on the border with China, very close to India, and we're going to visit Chipui Pangwa, right on the Chinese border. Myanmar contributes about 8% of heavy rare earth supply in the world, and we look down at Chipui Pangwa on the Chinese border, where rare earth mining has absolutely boomed, supplying heavy rare earth is essential for Chinese magnets. The sites are controlled by armed groups exporting those concentrates to China. Dysprosium, terbium are the main rare earths, but conflict disrupts the stable supply chain. Mining has expanded very rapidly since the 2021 coup d'etat, but the environmental damage has been severe and there's been very little environmental regulation. Trade paused again in 2024 when military control seized that part of the world. This has pressured China, and negotiations reopened the border trade under new levies. Myanmar's rare earths output are critical for global supply, but it highlights the security risk and the geopolitical leverage in this mineral supply. No tour would be complete without a visit to Greenland, so Jared, why don't you take us there next?
Greenland represents one of the world's highest potential frontiers for rare earth elements, especially heavy rare earths. Several deposits rank among the largest known globally, drawing strategic interest from major powers. But geology in Greenland runs far ahead of development. There's no commercial production today, and projects face harsh Arctic logistics, high costs, limited infrastructure, and short construction seasons. Environmental concerns play a central role in public debate, and mining decisions often become national political issues. Greenland's rare earth story is therefore about long-term optionality, shaped by the ongoing tension between development, environmental protection, and geopolitics. Tambrise is Greenland's most advanced rare earth project and the only one with a full exploitation license. It's hosted in a large peralkaline intrusive complex with rare earths primarily contained in eudialyte, a mineralization style that's distinct from monazite or ionic clays. It contains one of the world's largest rare earth resources by tonnage and a meaningful proportion of heavy rare earths. Early productions targeted later this decade, supported by Western strategic interest and financing discussions. Other projects, including Kienefeld, remain stalled due to political and environmental concerns. So Tambrise represents Greenland's only credible near-term pathway into rare earth supply, while broader development depends on resolving long-standing economic and environmental tensions. Now I'll hand back to Andy to take us home.
We conclude our tour today with 7 takeaways. We've clearly seen that rare earths matters less by mass and more by leverage in magnets and motors and advanced electronics. That the real choke point is separation of metals and magnet making, not in the mined ore itself. That neodymium and praseodymium and dysprosium and terbium drive the energy transition urgency. Most of the other rare earths are basket byproducts. We've seen repeatedly that China dominates through integrated clusters in the downstream, but also powerful in the upstream. That diversification by other countries requires years of industrial build-out, and that new nodes in the United States, Canada, Australia, India, and Brazil do help to reduce risk, but that heavy rare earth supply remains very fragile. I hope you enjoyed the tour today. Join us again next time.